This is Mrs. O'Neill for AP Chemistry, Chapter 11, Section 1, Liquids and Intermolecular Forces. The lotus plant grows in aquatic environments. In order to thrive in such an environment, the surface of a lotus leaf is highly water repellent. Scientists call surfaces with this property superhydrophobic. The superhydrophobic character of the lotus leaf not only allows it to float on water, but also causes any water that falls on the leaf to bead up and roll off. So please look at those terms on page 452. And in December of 1968, when the Apollo 8 astronauts first saw their home planet from a distance of thousands of kilometers, they affectionately called it the Big Blue Marble. Water covers about 3/4 of Earth's surface. In addition to making up Earth's oceans, water forms the polar ice caps and cycles through the atmosphere. All life forms that are known to exist are made mostly of water. In this section, you will learn about the properties of water and what makes this unique substance essential to life on Earth. In Section 1, it's titled A Molecular Comparison of Gases, Liquids, and Solids. So Mr. Anderson did a nice job, hopefully explaining to you solids and liquids and some of their properties. So water is both liquid and solid phase in this class. He gave you a nice Venn diagram. He also went through that PhET simulation and how these phases and molecules move in those phases of state, solid, liquid, and gas. He talked about solids and how their specific matrix can be amorphous, which means there's not really a specific pattern and they can easily break, or it could be crystalline and that arrangement of those atoms are like a repeating pattern and you can get something as strong as a diamond. He talked about the translational movement. He talked about viscosity and how viscosity is how easily a liquid can flow. And the higher the viscosity means that it's thicker. I guess that's the easiest way to say it. The higher your viscosity, the thicker the liquid is, so it's going to flow slower. Talked about surface tension, and a lot of this is going to be based on IMFs, and we're going to learn a little bit more detail about that later in this chapter. He talked about mixing of the water and ethanol and how they actually fit inside each other. So I actually do this lab in my applied class, and I take 25 milliliters of water, 25 milliliters of ethanol, and when they mix it, they don't get the 50 milliliters of the mixture that they assume. That's because the water and ethanol are kind of fitting inside each other's spaces. So again, a nice review of those three topics. He also went to talk about the heating curve. Again, something else we're going to talk about in more detail in the coming sections. But he talked about how this area is ice as we're heating up the H2O. Then at some point, the ice and water exist simultaneously. Then we have water as we go through that liquid phase. And when we're in liquid/gas or vapor phase, again, it's done at the same boiling temperature. And then we have vapor. So here, your melting and freezing point is the same. To freeze water or to melt ice is going to be 0 degrees Celsius. That is the same temperature, as well as your boiling point of 100. So going from water to gas or gas to water, it's going to be 100 degrees. So onto your notes packet. Again, I suggest filling in the blanks, pausing the video, and then play to hear my words. So your objective really is to compare these solid, liquids, and gases from the molecular perspective, not things that we can see with the eye, but what's really going on inside with those atoms and molecules. And this is going to play important roles about temperature and those IMFs, and of course determines the physical state of that substance. So liquids and solid properties versus gases. Not much to say except for understanding what these mean and why liquids and solids are incompressible versus gases are compressible. Liquids and solids molecules stay close together, where the gases, those molecules are all over all over the place. Liquids and solids density really doesn't change much with temperature. So if I have a solid piece of any metal, that solid piece of metal, that density is going to be the same whether I have it in my cold refrigerator or if I'm going to put it outside in the sun on a warm summer day. Where the density, though, of gases is going to be very temperature dependent. Liquids and solids will have these intermolecular forces of attraction, where gases, not so much. We are going to talk about how they have a little bit of attraction, especially when we bring those gases and cool them down and we get them more like a liquid phase. But gases, for the most part, we're going to say are ideal. And if they're ideal gases, that means they're not attracted to each other. So again, solids and liquids have that intermolecular attraction, which means solids, again, those dotted lines are representing those intermolecular attraction. And IMF is the attraction between one molecule and another that's close by. In a liquid, again, if you notice, we have those IMFs. Again, we have those positives to negatives, negatives to positives. They're going to move around more freely, but they still are going to have those IMF attractions with each other. So we want to remember that a solid has a definite crystalline structure. Liquids are going to have different IMFs, and that's what most of this chapter is going to be about. And of course, gases, we already talked about how there's an ideal gas versus real gas and what the differences are. So what is the main difference between intra, RA, and the inter, ER? Intra is basically the bonds between atoms within the molecule, and inter is really the force of attraction between those molecules. So I like to remember international, right? International, you have many different countries that maybe are touching each other, especially like in Europe, you know, when you're going from Switzerland to Spain to Italy to Greece, all of those, right, they're all international. They're in between countries. But if you live inside Italy, you're an Italian, and that would be an intramolecular force, right? Those are all Italian people. So if you want to kind of think of it that way. And again, the strength of attraction of these IMFs, of course, are going to be, gas is going to be the weakest, liquids are going to be somewhere in between, and then, of course, you have your solids that are going to have the strongest intermolecular forces among the molecules and atoms that are there. But these liquids, again, because the liquids is a wide range, right, gases are all over the place. Solids, the atoms and molecules are really, really close together. It's these liquids, and that's why this chapter is a little confusing. It's these liquids that have a wide range of different IMFs that are going to tell us how strong or weak they are. See you in class.